Welcome back to the Deep Dive, where we carve out the essential wisdom from the most dense technical blueprints. Today, we are taking on an infrastructure problem that it's plagued the fastest-moving companies for years. I'm talking about the monumental operational complexity required to deploy sophisticated AI models at scale.
It's the MLOps bottleneck. And it's a source of, genuine pain for so many teams. Engineers spend just countless hours wrestling with cloud infrastructure. They're debugging these brittle Docker files, trying to translate Python requirements into, obscure Kubernetes manifests, managing GPU drivers.
Across all these different machine images, right?
Exactly. And that friction, it just severely hampers the ability of an organization to move quickly. You end up forcing this really valuable talent to act as glorified systems administrators.
Instead of what they should be doing.
Instead of focusing on model iteration and optimization.
That is the core issue, isn't it? The gap between having a model that works beautifully on your laptop and then getting it running reliably, affordably, and scalably in production. That gap can swallow months of development time.
It really can.
But our source material today introduces a pretty radical new solution. It's a platform called Modal, and it promises to redefine this entire process. The core philosophy is actually quite simple. It's your infrastructure is code, defined entirely in Python.
And for anyone who has spent a sleepless night trying to figure out why their container image works locally but then just fails spectacularly on a cluster.
We've all been there.
That phrase is not just a promise, it's a relief. It's a huge relief. By embedding the infrastructure definitions right into your application code, Modal is aiming for perfect reproducibility. And that drastically reduces the burden on MLOps teams. It completely abstracts away the operational heavy lifting of containerization, scaling, and all that hardware provisioning.
Okay, let's play devil's advocate for a second here.
Yeah.
We've seen other serverless platforms, and they often lead to some kind of vendor lock-in, or they force developers into these really proprietary configurations. So what are the key features of Modal that make this Python-defined paradigm a true game changer for you, the listener, who really values speed and cost efficiency?
I think it boils down to three really compelling hooks. First, zero configuration. And this means the total elimination of YAML.
No more YAML.
No more Kubernetes manifests or specific cloud SDKs for orchestration. You manage the entire stack in standard version-controlled Python.
Okay, that's huge. What's number two?
Second, full serverless execution. And this comes with the crucial per-second billing. So you are not paying for idle GPU time. You only pay when your function is actually running. The system automatically scales down to zero.
And the third hook, which is, this is absolutely critical for the AI space, is the simplified GPU access. You can provision the most sought-after, cutting-edge hardware. We're talking H100s, A100s, even B200.
With a single parameter.
In a Python decorator. That level of hardware abstraction is pretty much unheard of.
It truly is. And strategically, this shift is vital because of something called resource pooling. Modal pools compute capacity across multiple major cloud providers. So this isn't just about convenience.
Right, it's about optimization.
It's dynamically optimizing for the critical factors in AI deployment, achieving high GPU availability, cutting down on those long provisioning wait times, and securing the best cost effectiveness in real time. This dynamic optimization frees engineers from that manual allocation struggle.
And all the cloud-specific procurement hurdles.
Exactly.
This sounds like complete re-architecture of the MLOps pipeline.
Oh.
So our mission today is to give you, the listener, a thorough technical roadmap. We are going to deconstruct the three core building blocks, the app, the image, and the function. And then we're going to walk step by step through the specific architectural patterns that enable scalable AI. We'll cover high-throughput GPU inference, resilient job queues, and of course, massive parallelism.
We're basically charting the path from a simple Python script on your laptop to a massively scalable, production-ready serverless service in the cloud. And the key is, it's defined entirely by objects and decorators you are already familiar with as a Python developer.
All right, let's unpack the architecture. I kind of like to think of building a Modal application like following a complicated recipe to produce, a scaled-up product. If you can understand the fundamental relationship between the three core building blocks, the app, the image, and the function, you've pretty much mastered the Modal paradigm. We're calling this the Trinity of Concepts.
It's an excellent analogy. It really is, because each component serves a distinct, necessary role in the execution environment.
Let's start with the largest container then. One, the Modal.app. This is the entire recipe book, you could say. It's the binding that holds everything together. It acts as the shared namespace for your application, and it manages the life cycle and deployment of all the resources. So functions, secrets, volumes, everything you define within that single deployment unit.
Right. And next, you need the environment to actually execute that recipe. So the modal.image. This is your kitchen setup. It's the programmatic equivalent of a custom Docker container, but, and this is the key, it's defined in Python.
No Docker file.
No Docker file. It dictates the operating system base. Often you'll start with something lightweight like Debian Slim. And crucially, it defines all the system libraries and Python packages your code relies on. This is where Modal guarantees environment reproducibility. It finally solves that frustrating "it works on my machine" problem.
And finally, the instructions themselves. 3, at app.function. This is the real power tool. It's the primary decorator that takes any standard Python function you write and just transforms it into a remotely executable serverless unit of computation. This function is what Modal scales, what it builds for, and what it runs inside the environment defined by the image.
Exactly. The relationship is hierarchical. The app organizes, the image provides the isolated environment, and the function is the scalable, defined task that gets executed within that environment. But to use this effectively, we really have to delve into the two distinct application lifecycles. This is a point where I find a lot of newcomers get a little tripped up.
And this distinction is so crucial for your development flow. You've got this temporary rapid iteration environment and then the persistent production environment.
Precisely. First, you have the ephemeral app. This is what runs when you execute the modal run command in your terminal. And it is strictly temporary. The entire application exists only for the duration of that script's execution.
So it's perfect for development.
Perfect for development, debugging, interactive data manipulation, or just running a one-off batch job. And crucially, when your client script finishes, Modal automatically and instantly tears down all the associated cloud resources.
So no cleanup required.
No cleanup, and therefore no unexpected billing, which is key.
And then we have the production standard, B, the deployed app, which you create with Modal deploy.
This application is persistent. It lives in the cloud indefinitely, ready to respond to requests, whether they come from a cron scheduler, an internal API call, or some external webhook.
Right.
And critically, when you update a deployed app, Modal handles the change seamlessly. If you rerun Modal deploy with code changes, the platform executes this version 0 downtime update. It ensures that your production service remains continuously available while the new containers are warming up.
That's a huge operational burden just lifted from the developer.
It's entirely abstracted away.
Okay, let's make this concrete. Let's use the Hello Cloud example from the docs, but let's go deeper than just showing the code. I want to talk about how that code gets from your laptop to the cloud, especially the role of that .remote call.
Great idea. So when you write an app.py script, you define the remote function, let's say def square x.returnxx, and you decorate it with @app.function. Then you define your entry point using @@.localEntryPoint. Now this is the function that actually executes locally when you run modal run app.py. Inside that local function, you invoke the remote capability by calling square.remote5.
Okay, so if I call remote, what is the Modal client on my laptop actually serializing and sending up to the cloud? It has to be more than just the arguments, right? It's not just sending the number 5.
Oh, it's much more complex. When .remote gets called, the client on your machine is the orchestrator. It performs 3 crucial serialization steps. First, it captures the code closure, it packages up the function definition itself, and any variables or imports it needs from its surrounding scope.
The whole context.
The whole context. Second, it references the execution environment. It points to the specific modal image you defined, which details the OS and all the dependencies. And third, it sends the runtime context, which includes the arguments, like 5 in our example, and any configured one-time requirements, like the GPU spec or memory allocation.
That's the key synthesis right there. The local entry point stays local, acting as the conductor. It manages the flow. But that remote method, that's the trigger. It kicks off the entire packaging, transmission, and execution process in a fresh, isolated container in the cloud. And it's automatically handling all the containerization and scaling needed to execute that remote task.
And the beauty of it is that you, the developer, only write the single app.py file and you run one simple CLI command, modal run. Modal manages all the complexity of environment capture, dependency resolution, and remote execution completely transparently. So for you, the listener, recognizing that moment when the local Python object transitions to a serverless cloud execution, which is always defined by a .remote or spawn call, that is the foundation of architecting on this platform.
All right, so now we get to address the infrastructure problem that keeps AI engineers awake at night. Reliably provisioning, and more importantly, paying for elite hardware. We've established that requesting an H100 is just a decorator parameter, but let's look at the immense complexity that single parameter is replacing.
It replaces weeks of work. I'm not exaggerating. Instead of navigating cloud console menus, writing Terraform, configuring private subnets, installing specialized drivers,
The whole 9 yards.
you just define your need in Python at app.function GPU A100. That one instruction tells Modal to find the optimal machine in its multi-cloud pool that meets this requirement, launch the environment, and execute your code.
Okay, so let's talk about building the necessary environment for modern AI. I mean, a basic slim image isn't going to cut it for large language models, for LLMs. We need a highly specialized setup.
Absolutely. The image definition has to be precise. You'll start with a base image, maybe modal.image.debian slim, Python version 3.1, and then you chain on your dependencies. For a typical LLM stack, you might use something like .uv pipe install, transformer storage, accelerate, bit sandboxes.
You specifically use pipe install there. Why is that little detail about dependency resolution so important?
This is a critical performance detail. It contributes directly to developer velocity. Tools like Ev, which is a very fast Python package installer and resolver, significantly accelerate the image build process. When you're iterating rapidly on a model or a dependency chain, shaving minutes off the image build time means faster CI/CD cycles and a quicker path to production.
And with AI, those environments can be massive and complex.
Exactly. So optimizing this step is paramount.
And of course, if we're pulling models from, say, Hugging Face or accessing private data sources, security is non-negotiable. How do we securely manage sensitive data like API keys without committing them to our image or our source code?
That's managed through Modal's secrets mechanism. When you define the function, you pass a reference, something like secret_modal.secret.fromName, Hugging Face access key. This securely injects the sensitive data, like an API token, as an environment variable directly into the runtime container.
So it never touches the code repo.
It never appears in your code repository, your image layers, or your logs. It meets really strict compliance requirements for production services.
Let's get granular on the hardware options, because cost and performance analysis often hinge on choosing exactly the right card. What are the key GPUs available, and what are the trade-offs we should be thinking about?
Modal supports a pretty wide spectrum, which caters to different cost and performance needs. At the entry level, you've got the T4, which is suitable for lighter workloads. Moving up, you'll find the L4 and the A10. And then for high-end dedicated AI work, the A100 in both 40 and 80 gigabyte VRAM versions is a workhorse. But the newer generation cards, the L40S, H100, H200, and B200, that's where the real optimization opportunities lie.
Okay, so if I'm an architect and I need to maximize inference throughput for an LLM that requires a really large context window, which card is going to give me the best combination of memory capacity and value?
The L40S is frequently cited in the sources as the go-to recommendation for high-throughput inference.
Why that one specifically?
It offers an excellent cost-to-performance ratio, and critically, it comes with 48 gigabytes of GPU RAM. For deploying large transformer models, having that large VRAM capacity minimizes the need for complex quantization or model splitting, which directly reduces your latency.
What if my application needs multiple GPUs? Let's say for distributed fine-tuning or running a model that exceeds even 80 gigs of VRAM.
In that case, you use the multi-GPU syntax, GPU H100.8. This requests 8 H100 cards, and Modal guarantees they'll be interconnected on the same physical machine with high-speed NVLink.
Okay, but there has to be a catch.
There's a vital operational note here. Requests for more than 2 GPUs per container often involve significantly longer queue and wait times. It's just much harder for any cloud provider to provision these big multi-GPU instances on demand.
So the advice is,
If you can distribute your workload horizontally instead of consolidating it vertically, you'll likely achieve lower overall latency by scaling out.
that brings up a critical point about dynamic hardware management. The sources mention that Modal might automatically upgrade H100 requests to H200s. Why does it do that, and why might a developer actually want to prevent it?
This is a great example of that dynamic optimization. Modal is leveraging cloud availability to improve your performance for free. The H200 offers, I think it's 1.75 times larger memory capacity and 1.4 times faster memory bandwidth than the H100.
At the same cost.
At the same cost point. Modal will automatically use it if it's available. The only reason you'd prevent this, and you can by using the H100 suffix with an exclamation mark, is if you were running very strict benchmarking tests and needed absolute consistency in hardware specs.
Okay, let's pivot to the really deep analysis of bottlenecks. Before a company commits a massive budget to the latest B200, what critical thought process should the architect apply? You mentioned earlier that some AI tasks are memory-bound.
This is the conversation that saves architects millions of dollars.
I'm listening.
When you're running LLMs, particularly those responding to a single small prompt, the workload is overwhelmingly memory-bound, not arithmetic-bound. Arithmetic throughput, or FLOPS, has accelerated dramatically, but the rate at which the GPU can fetch weights and activations from its VRAM, the memory bandwidth, that often remains the primary bottleneck for low-latency inference.
So just to be clear, using a highly expensive B200, which has phenomenal arithmetic power, might not actually reduce the latency of a single prompt if the limiting factor is just how quickly it can pull the 48 gigabytes of model weights.
Exactly. The delay is often determined by latency in accessing that VRAM. If an L40S can comfortably hold the 48 gig model weights in its fast memory, the incremental speedup you'd get from the B200's faster tensor cores might be marginal relative to the huge jump in cost.
So what's the smart choice?
The smart choice is often the L40S or an 80 gig A100. You're balancing cost, memory, and arithmetic capability precisely to address the actual bottleneck of your specific inference pattern.
So the takeaway is, always benchmark against memory performance before assuming more FLOPs is the answer.
Absolutely. So having tackled the complexity of single container GPU performance, let's now transition to managing high volume and resilience. We're talking about the problems of distribution and asynchronous processing. And these are solved, I think, beautifully with two distinct Python native patterns.
Let's start with pattern 2, Asynchronous Job Queues. This is the standard solution for applications that need to maintain immediate responsiveness while kicking off tasks that might take seconds, minutes, or even hours to complete.
Right. The primary use case is offloading these long-running tasks. You can have up to 1 million of them. And you're offloading them from a responsive front-end application like a web API. Modal effectively eliminates the need for external queuing systems like RabbitMQ or Celery by integrating the queuing mechanism directly into the function invocation itself.
Okay, walk us through the 3 steps needed to implement this pattern.
Step 1, define and deploy. You define your worker function, maybe it's process video file, and you deploy it persistently using Modal deploy. This makes it available as a scalable worker service in the cloud. Step 2, submit non-blocking. From your primary application, say a fast API server, you submit the job using the spawn method, processvideo.spawn data. Now this call returns immediately, it does not block, and it gives you back a unique string handle, the call.objected.
So that ID is basically the receipt for the job. It lets the caller check back later.
Precisely. Which brings us to step 3, poll for result. The caller uses that ID to query the job status.modal.functionCall.fromMid, call it, followed by .get timeout5. By setting a low timeout, the polling endpoint ensures it quickly reports the status without blocking its own thread.
The resilience here seems exceptional. How long are these job results maintained, and what happens if a job takes too long?
Yeah, the sources highlight really robust reliability. The results of a spawn call are persisted, and they're accessible for up to 7 full days after the job completes.
Wow, 7 days.
It gives you a very generous window for clients to retrieve results, even if they experience temporary outages.
And the errors.
If the client tries to get the result before it's ready, the polling function will raise a standard Python timeout error. If they try after that 7-day retention window, they get a modal.exception. Output expire error. Modal just manages all this state for you.
Let's talk about the production integration, because a clean HTTP interface is key for this stuff. If I'm running a fast API web server, how do I structure my endpoints to use this non-blocking pattern effectively?
Good question. In a typical FastPI setup, your submission endpoint would use the asynchronous version of the API, so await process job.spawn.aio data. It submits the job and immediately returns a JSON response that contains the objected. Then you'd have a second endpoint, maybe result called, to handle the retrieval. That endpoint uses await function call.get.aio timeout 0.
A 0 timeout. Why a 0 timeout?
A 0 timeout means check immediately, but do not wait if the result isn't ready. So if the result is pending, your fast API endpoint would be programmed to respond with an HTTP 202 status code, which means accepted, pending.
And if it's ready.
If the result is available, it returns a 200 OK. If the call ID isn't found or it's expired, it returns a 404. This pattern ensures the web server is never tied up waiting for a long process. It gives you a highly scalable and robust interface for these intensive computational jobs.
Okay, so now that we know how to manage high volumes sequentially, let's move to distributing the workload horizontally across, well, potentially thousands of containers simultaneously. This is pattern 3, massive parallel processing with .map.
This is the high-level API for large-scale batch jobs. It's indispensable for massive data processing, running millions of independent model inferences, or conducting large-scale hyperparameter sweeps like a grid search. It's really designed to replace complex, manually orchestrated parallel frameworks.
What does that high-level API look like, and how does Modal handle the orchestration underneath?
It's remarkably simple. If you have a function, say process datum in petrichord, and a list of 1 million inputs, you just write results, this process datum.map, list of inputs. Modal takes this list of inputs and automatically performs the fan out.
So it splits the list, distributes the work.
Exactly. It distributes the work across a potentially enormous number of containers, managing all the concurrent scaling. Then it manages the fan-in, collecting all the results, and it returns them as an iterable that's guaranteed to be in the exact order of your original inputs.
That ordering guarantee is a huge benefit for data pipelines where integrity is critical. What about functions that need more than one input? Like if I'm optimizing a model and I might pass a learning rate and an epoch count.
For functions with multiple arguments, you use function.starmap. This mirrors the behavior of Python's itertools.starmap. You pass a single iterator of tuples or sequences, and Modal unpacks each item into the function's required arguments before it distributes the job.
Okay, so what if, out of my 1 million inputs, 50 of them trigger some unexpected bug, or they fail because of corrupted data? Does the whole parallel job just crash and burn?
By default, yes. If any single parallel call raises an exception, that exception is immediately propagated back to the main client, and it halts the entire mapping process.
But there's a way around that, I assume.
There is. For resilience in data pipelines, you can pass the argument return exceptions, true to the .map. This tells Modal to treat the exception as a return value. It collects it in the results list instead of raising it.
So then you can just iterate over the results later.
Exactly. You iterate over the results, check which entries are exceptions, and then you can handle or retry those specific failed inputs without losing all the work from the other 999,950 successful containers.
That's a crucial design consideration for building robust pipelines.
Yeah.
Finally, what are the common developer pitfalls when they're using .map?
The gotchas. The sources outline 2 main gotchas. First, do not confuse function.map with Python's built-in map. Python's version runs sequentially. You must use the explicit modal object method to get the distribution and concurrency. Second, remember that .map operates on the function object itself. A common mistake is trying to call the function first, like evaluate model inputs.map.
Oh, I can see people doing that.
Right. You must call evaluate model.map, list of inputs. If you do the former, you'll just be mapping the single return value of a local function execution, which completely defeats the purpose of massive parallel scaling.
Right, got it. We've established how to deploy code and manage massive volume. Now let's focus on the nuances of production operation. Fine-tuning scaling for specific latency targets and optimizing costs. Modal gives developers control over the auto-scaling pool far beyond the standard scale to 0.
Yeah, every function has its own auto-scaling logic built in. And while scaling down to 0 is the cost-saving default, high-traffic or latency-sensitive applications really need a warm pool of containers. This is all managed through specific parameters you pass to the @app.function decorator, which lets you balance latency and cost with real precision.
So let's define the parameters that control this warmth. What are they?
The key settings are max containers, which sets the hard upper bound for scaling. Then there's min containers, which defines the size of the warm pool kept running even during inactive periods. This is your primary latency reduction tool.
Okay.
Then you have buffer containers, which maintains a surplus of idle capacity while traffic is active, preventing spikes from hitting a cold start. And finally, scale down window, which determines the maximum idle time a container is allowed before Modal terminates it.
Let's run a quick cost scenario. If I'm running a latency-sensitive API on A100 GPUs and I set min containers 4, I'm paying for those 4 machines 24/7, right? Even overnight, just to guarantee zero cold starts at 3 a.m. That's
Yeah.
expensive.
That is the core calculus. Let's assume an A100 costs roughly, what, $250 to $350 an hour in a pooled serverless environment. Keeping 4 warm containers costs $10 to $14 per hour.
Which is $240 to over $300 a day.
Just for standby capacity. The trade-off is measurable. If a cold start introduces 5 seconds of latency and your business can tolerate that cost during off-peak hours, you set min containers to 0. But if 5 seconds of latency during peak hours means lost revenue or customer churn, you absorb the cost and you keep the pool warm.
That financial calculation is usually manual, though, and it often requires a full redeployment to change. But the sources noted that Modal allows for dynamic adjustment of these warmth settings. How does that work?
This is a really powerful feature. It's done using the function.updateAutoScaler method. A function can call this method on itself or on another deployed function to adjust parameters like min containers on the fly.
Without a full application redeployment.
Without a redeployment.
Can you give us an operational example of how a developer would actually use this?
A standard pattern is to define a separate, lightweight function that's scheduled to run via a cron job. This scheduled function executes twice a day. At 6 a.m., it calls my inference function.updateAutoScaler min containers 4.
To prepare for peak traffic.
Exactly. And then at 10 p.m., it calls my inference function.updateAutoScaler min containers 0. This maximizes responsiveness during the day and it minimizes cost overnight, all defined in just a few lines of Python.
That's infrastructure automation defined in application logic.
That's wild. Okay, let's move to concurrency within a single container. When is input concurrency useful and when is it a performance risk?
Concurrency within a container is beneficial when your tasks are I/O bound. That means they spend most of their time waiting for external data. This includes things like querying external APIs, waiting on database lookups, or critically in AI, when you're performing continuous batching on a GPU where the forward pass is fast and the container is just waiting for the next input batch.
So concurrency lets you maximize the utilization of that expensive resource.
That's the goal.
How is it enabled? You use the @modal.concurrent decorator. You set max inputs for the hard limit of simultaneous inputs the container will process, and target inputs to guide the autoscaler on the desired optimal load. So for example, setting max inputs 120 gives you a burst capacity above the target inputs 100 that the autoscaler typically aims for.
Okay, let's dive into the critical technical risk here. The difference between synchronous and asynchronous functions, and how Modal implements concurrency for each. This really touches on fundamental constraints of Python itself.
This is a deep dive moment for sure. If you define a synchronous function, a standard def, Modal achieves concurrency using separate threads. This means your function must be thread safe. For Python, this is complicated by the global interpreter lock, the GIL.
Right.
Now, while the GIL makes CPU-bound tasks run sequentially on a single core, it does release the lock during blocking I/O operations, like network calls. So synchronous functions relying on heavy I/O can benefit from threading, but you have to be extremely careful about shared state and race conditions. It's complex to debug.
In contrast, what happens if I define the function as async def?
If you define an asynchronous function, Modal uses separate asyncio tasks, all running on a single thread. Tasks are cooperative. They yield control back to the event loop whenever they hit an await call. This is generally safer because there's no true context switching between simultaneous executions of Python bytecode.
But there's a different risk.
The risk shifts. You must absolutely ensure your async function doesn't execute any blocking, long-running CPU code. If it does, it will stall the entire event loop and defeat the purpose of concurrency.
That distinction is paramount for stability. Speaking of stability, let's address the gotcha of logging in a concurrent environment.
It's a huge one. When you have 100 threads or tasks all writing to the same standard output stream, the logs just become a chaotic mess. It's nearly impossible to trace a specific failure back to its input.
So what's the solution?
The solution is to use a unique input identifier. You can either generate one manually, or even better, use modal.currentIntuited within your function and ensure every single log message includes that ID. This lets you use the Modal dashboard search or external log processors to filter logs by that specific invocation ID.
Moving finally to image management and speed. Building complex, multi-gigabyte AI environments takes time. How does Modal help developers control their image sources and ensure the absolute fastest pull times to minimize cold start latency?
You have 3 main ways to define your environment programmatically. The most common is defining a base and then chaining commands, like .debianslim.pig-install. Second, you can pull from a public registry with image.fromRegistry, name.tag. And third, for proprietary images, you can pull securely from private registries, like Docker Hub or AWS ECR, by passing a modal secret that contains the authentication credentials.
And what if my chosen base image, maybe an older Ubuntu release, doesn't have a modern Python setup? Can Modal still use it?
Yes. If the base image doesn't meet Modal's requirements for executing Python functions, you can add an add Python argument, something like modal.image.fromRegistry, Ubuntu.22.04 add Python 3.12. Modal will then automatically install a clean, reproducible, isolated Python environment for you right inside that image.
Let's finish this section with the crucial performance optimization, eStargz. This is highly technical, but it's fundamental to achieving low cold start latency for large AI images. Can you give us a clear metaphor for how eStargz works?
Okay, think of a 50-gigabyte model image as a massive 4K movie file. Traditionally, a container runtime has to download the entire 50-gigabyte file before it can start playing the movie. That's full downloading. eStargz compression, which uses lazy pulling of layers, is like streaming that 4K movie. You only download the crucial beginning layers, the OS and the Python environment, right away. The large layers containing the model weights are streamed only when the function execution actually calls for them.
So instead of a 10-minute download, I get an almost immediate cold start because the environment is ready instantly, and the massive model weights are just pulled in just in time.
Precisely. This dramatically reduces the initial perceived load time. Now, to enable this, if you're building your own images, you have to use BuildKit version 0.10.0 or higher and pass specific flags during the build process, things like compression eStargz and OSI media types true. This ensures your image layers are compressed in a way that allows this lazy streaming access by the runtime. It's a technical detail, but it's a direct optimization for AI services that prioritize low latency.
Okay, so we've built, we've scaled, and we've optimized performance. Now we look at the requirements for true production readiness, resilience, zero downtime updates, and critically, security protocols, especially for running code generated by AI agents.
Right, the operational cornerstone is modal deploy. What is the mechanism Modal uses to ensure that when I push an update, there's absolutely no disruption to my live service? Modal employs a zero downtime update strategy, which is very similar to a blue-green deployment. When you run modal deploy, the existing application version, let's call it the blue environment, continues serving all live traffic. Concurrently, the new version, the green environment, begins building its image, configuring its functions, and warming up its containers in the background.
When does the traffic actually shift? And what happens if the new version is faulty?
The traffic shift only occurs once the new green containers pass a mandatory set of health checks and are confirmed to be fully operational and ready to accept requests. If the new containers fail that health check, maybe the code throws an exception on initialization or dependencies aren't loading, Modal halts the deployment and retains the stable blue version as the live traffic handler.
So it's safe.
It's safe. And once traffic shifts successfully, the old blue containers are allowed to finish processing any in-flight requests gracefully before they are terminated, which guarantees continuity.
And if a major bug makes it through all that, is a rollback possible?
Yes. Rollbacks are treated as a special type of deployment. You simply instruct Modal to revert the application's configuration and function definitions to a previous, known good version. This is critical for maintaining your service-level agreements, though the sources do indicate this specific feature is currently available on the higher-tier plans.
Okay, let's move to one of the most pressing architectural challenges in the age of generative AI, secure execution of untrusted code. As LLM agents gain the ability to generate their own functions, we need really robust isolation mechanisms, and Modal offers two primitives for this.
The first is the simpler approach, restricted functions. You just apply the decorator, restrict modal access. True. These functions are highly isolated and they're stateless. They are prevented from calling other modal functions, accessing modal resources like volumes, or using any internal APIs.
So they're good for what?
They're perfect for quick one-off execution of user-submitted code or generated snippets where you need maximum isolation and minimal overhead.
And the second, more powerful primitive is the sandbox.
The sandbox provides a fully defined, stateful, container-like environment for running arbitrary commands using methods like sandbox.exec command. It's built for interactive execution, running non-Python arbitrary binaries, or executing long-running scripts generated by an agent. And critically, the sandbox supports the full set of function configuration, including custom images, secrets, and volumes. This allows an agent to define a complex, necessary environment and run its code within that context.
So if an architect chooses to run untrusted or generated code, even within these isolated primitives, there are 4 mandatory security best practices that cannot be ignored. Let's detail those because they are essential for data safety.
These are non-negotiable security requirements. 1. Set max inputs 1. This ensures every single untrusted execution runs in a fresh, brand new container instance. This prevents sensitive data, environment details, or authentication artifacts from leaking or being accessed by a subsequent, potentially malicious request that ends up in the same container cache.
Right, a fresh container per request prevents side channel attacks through cache memory. What's step 2?
2. Use aggressive timeout settings. Untrusted code can maliciously or just accidentally enter an infinite loop or attempt to engage in resource exhaustion attacks. Setting a very low, strict timeout immediately halts processes that exceed expected runtime limits. It safeguards your compute resources and your costs.
And for network safety.
3. Use block network. True. This is a powerful safety net. It completely prevents the container from making any outbound network requests. This stops data exfiltration attempts, command and control communication, or connections to external attack infrastructure. It just locks the code into the Modal environment.
And finally, controlling the code itself.
4. Minimize the source code included in the container. If you are running an isolated function, its image should only contain the absolute bare minimum necessary. Don't include sensitive business logic, database wrappers, or complex application code in the image if that code isn't required for the untrusted function. This reduces the attack surface and minimizes the potential impact if the container is compromised.
Those 4 practices are the foundation for secure AI deployment. Okay, finally, let's discuss internal communication between services. In complex microservice architectures, Modal offers an alternative to writing complex HTTPS interfaces for every service-to-service call.
This is inter-application communication using the native Python lookup mechanism. Instead of hitting a public web endpoint, one deployed Modal app can call a function in a completely separate, independently deployed Modal app. It's done with modal.function.fromName, app name, function name.
What are the benefits of this internal Python invocation over standard HTTPS or API calls?
The advantages are pretty significant. First, you bypass writing any web endpoint boilerplate, no URL routing, no HTTP methods to define. Second, Modal automatically handles data serialization for the Python objects being passed, which eliminates manual JSON or protocol buffer conversions.
That's nice.
Third, it leverages Modal's built-in authentication layer, so the communication is implicitly secure without needing to manage internal API keys or token rotation. And fourth, the function lookup is internal and secured, ensuring your services aren't exposed to the public internet, unlike a traditional web endpoint.
And once that remote function is looked up, what can I do with it?
Everything. The remote function object behaves exactly like a local reference. You can invoke it immediately using .remote, distribute work using parallel execution with .map, and you can queue long-running tasks using .spawn. It allows for highly flexible and resilient composition of complex workflows across decoupled services.
That was a comprehensive technical deep dive into the architecture of serverless AI with Modal. We've demonstrated how that initial pain point, the MLOps bottleneck defined by Kubernetes and brittle YAML, is completely replaced by a unified, version-controlled system defined entirely in Python.
The central value proposition is really about eliminating the undifferentiated heavy lifting. Modal handles the containerization, the scaling, zero downtime updates, dynamic GPU provisioning, concurrent execution. It lets engineering teams dedicate 100% of their effort to the actual AI model and application logic.
Let's quickly synthesize the core commands and concepts that represent the fundamental shift we discussed. First, the 2 life cycles.
Modal Run is for the ephemeral app, so testing, development, batch jobs that scale to 0 and automatically tear themselves down. And Modal Deploy is for the persistent app APIs and scheduled services that require continuous availability and those zero downtime updates.
And the effortless access to elite hardware?
The simple instruction at app.function GPU. This just abstracts away all the complexity of cloud provisioning, driver installation, and availability. It even dynamically optimizes requests from an H100 to an H200 when it's beneficial.
We've seen how advanced operational patterns like asynchronous job queues with Spawn, massive data distribution with .map, and dynamic cost optimization by adjusting container warmth are all controlled by native Python object methods and decorators.
It creates a seamless end-to-end experience. The platform automatically distinguishes between threading and Asyncio tasks for concurrency. It employs eStargz for immediate cold starts, and it provides robust primitives like the Sandbox for secure execution of even the most untrusted, agent-generated code.
Which brings us to our final provocative thought for you to consider. We spent a significant amount of time detailing the Modal sandbox, which securely executes untrusted code, and the dynamic nature of image definition.
Imagine this scenario. A highly capable LLM agent is given a complex task. It doesn't just write the Python code for the task. It dynamically defines the specific Python dependencies and system libraries it needs, and it writes the modal image definition itself, all based on its understanding of the problem.
So if that AI agent can then spawn a sandbox using that dynamically defined image, and then execute its own code within that secure, isolated, and scalable environment, all within the same unified Python framework, we are no longer just talking about AI writing software. We are talking about AI defining, configuring, and operating its own scalable cloud infrastructure.
That convergence, where the line between application code, infrastructure configuration, and operational deployment dissolves entirely, that's where the next exponential leap in AI development velocity is going to occur.
That's all the time we have for this deep dive. Thank you for joining us, and we look forward to the next complex topic we can simplify together.